Hello and welcome to the Technion Aerial System Flight Readiness Review presentation. In the next 15 minutes, we will give you a brief overview of the system built this year. Our team is combined out of two faculties from the Technion Israel Institute of Technology, the Faculty of Aerospace Engineering and the Faculty of Electrical Engineering. Now, we would like to present this year's team members. Adi Toporek, Undergraduate Senior Team Captain. Dolav Simon, Safety Pilot. Evgeny Gutnik, Graduate Student System Engineer. Jason Ben-Shitrit, Undergraduate Senior System Engineer. Ofir Milul, Undergraduate Senior Imaging System Development. Daniel Joseph, Undergraduate Senior Avionics Engineer. Ro'i Yudei, Undergraduate Senior Communications. Ohad Marcus, Undergraduate Senior Target Detection. Sigalit Greenberg, Undergraduate Junior Structure Engineer. Imrit Zror, Undergraduate Senior Interoperability Development. The Strix, the latest and most advanced UAV development from the Technion Aerial System team. The Strix is a fully autonomous platform that was designed to meet all of the AUVSI SUAS requirements. Since there is no suitable platform that meets the team's desired specifications, we built the platform from scratch, starting with an FRR system requirements review, continuing to PDR and CDR surveys, and then to the production process, which included the layup of the composite structure, installing internal components, and integration. This year's platform's features: a new tail design for higher lateral stability, a new camera pod to reduce UAV's cross-section, a new propulsion system to increase thrust to the weight ratio, a lighter and stronger all-composite structure in order to reduce weight while maintaining sufficient strength, and a new set of flaps to decrease the touchdown speed during autonomous landing. The airframe is comprised out of 6 segments: 2 wings, fuselage, tail assembly, top cover of the fuselage, and the camera pod. All segments were designed to be detachable and allow quick access to the inner components, easy transportation, and maintenance. Due to the complexity of last year's avionics and payload systems, and the fact that troubleshooting malfunctions was very frustrating, this year's Strix avionics architecture was developed according to modern LRUs, line replaceable unit method resembling real-life industry applications, in order to allow easy maintenance in case of malfunctions. Our avionics system is divided into 3 main sections. The avionic block contains the necessary components to control the UAV: PICSOC flight controller, GPS module for high accuracy navigation, Futobar receiver for communication with the safety pilot remote control, battle switch, a mechanical relay to allow manual takeover in case of communication lost with ground control station and the UAV, RFD 900, a long-range radio telemetry, LiDAR, laser-based altimeter for accurate altitude data. The payload block contains the necessary components for image processing: NVIDIA Jetson TX1 onboard graphics processing unit, running the automatic detection algorithms on board; Odroid XU4 onboard computer managing all system devices and in charge on communication with ground station devices; Ethernet switch, enabling fast IP-based network communication between system devices; Bullet M5, 5 GHz wireless radio connects the aircraft to the ground station network; Arduino Nano, sampling the camera flash trigger and calculating the exact shooting time for each picture to improve geolocation accuracy; PoE, Power over Ethernet, providing power and local network communications to the Bullet M5. The nose section contains the gimbaled Sony Alpha 6000 camera, high-end mirrorless camera, remotely controlled for taking 24 megapixel still pictures; Gimbal IMU, inertial unit to provide attitude states of the gimbal to reference with the UAV; Vector Nav, extremely high-performance GPS, aided inertial navigation system that combines MEMS inertial sensors for the use of target's geolocation; a pitot tube for airspeed indication. During the academic year, we performed over 25 flight tests that sum up to approximately 150 flight hours in which the abilities of our system were tested and the flight line crew members were trained. As a result, we're confident that we will succeed in all of the competition missions, aiming for top 3 in this year's competition. Autonomous flights. Autonomous takeoff attempted, high confidence. Autonomous landing attempted, high confidence. Waypoints capture attempted, high confidence. Obstacle avoidance. Stationary obstacles attempted, high confidence. Dynamic obstacles attempted, medium confidence. Object detection, classification, localization. Search area attempted, high confidence. Off-axis attempted, high confidence. Geolocation attempted, medium confidence. Air delivery attempted, medium confidence. Interoperability attempted, high confidence. During the development, we performed numerous kinds of experiments to evaluate and test our UAV structure, components, and ground station. Wing loading test. To evaluate our UAV survivability during flight, we've executed a loading test that simulates the aerodynamic forces applied on the wings during flight and maneuvering. We place sandbags along the wings of which the weight is distributed according to the vortex lattice method and demonstrated a maximum load of 3G. We were able to see that the wings withstand loads during flight and extreme maneuvers. Thrust test. After evaluating last year's flights, a crash of one of our platforms during a touch-and-go maneuver, and the increase in total weight, we investigated the cause of the crash and came to the conclusion that our propulsion system provides insufficient thrust-to-weight ratio. A new combination of motors, ESC, and propellers were tested while our goal was to increase thrust-to-weight ratio while maintaining adequate flight time to complete the competition tasks. Our new thrust-to-weight ratio is 1.46, which means we increased our thrust-to-weight ratio by 230% compared to last year's ratio. Wing skin strain test. An additional goal this year was to reduce the total weight of a UAV. One of the methods to accomplish this was by examining 3 types of composite sandwich skin for the wings: soft balsa wood core with thick cover, hard balsa wood core with thick cover, and hard balsa wood core with thin cover. And we performed 2 experiments on each of the samples to select the best composition for the skin of the wing. The first experiment was a strain test, and the second one was a 3-point bending test. Finally, we selected the hard balsa wood core covered with thin graphite epoxy layers. By this, we succeeded to reduce 450 grams per wing. Camera gimbal test. Structure-wise, we performed a finite elements analysis to make sure our gimbal will be strong enough to carry the camera and to bear the loads of the flight. Secondly, we calibrated our gimbal controller so the gimbal is stable and parallel to the ground, same orientation as expected during flight. To ensure proper operation of the gimbal during flight, we examined the gimbal's behavior on ground by checking roll and pitch maneuvering. We were able to notice the gimbal orientation during the disturbances, and we tuned the PID controller according to gimbal's offsets. After the ground test and PID tuning, we stepped towards flight test. During the flight test, we flew over targets and captured them while maneuvering, tested the quality of the pictures we got. We made additional tuning to the PID parameters until we achieved optimized gimbal response. Antenna tracker. To ensure maximal communication rate between the ground station and the UAV, spare a human operator, and prevent risk of radiation, we've developed an automated antenna tracker, which uses 2 DOF azimuth and elevation in order to always keep the airplane in front of the antenna. Autonomous takeoff. Prior to attempting an autonomous takeoff, several key configurations had to be taken into consideration. First and foremost, nose steering on runway has to be tuned in order to safely keep the heading on runway during takeoff. To safely allow the airplane to reach stall speed, we have set a gradual 30% per second throttle increase until it reaches to the maximum throttle. Additionally, the takeoff speed in which the aircraft will pitch up is set to 30 knots. Autonomous landing. Since the procedure of an autonomous landing is somewhat risky, we've added to the UAV a laser altimeter unit, which provides accurate altitude readings below 40 meters above ground level. We developed this capability very carefully by using a step-by-step approach. We started our test by using a cheap RC model aircraft, a trainer. we took the approach of observing a manual landing and extrapolating the landing parameters for Arduplane landing algorithm. Once we made successful autonomous landing attempts with the trainer, we continued and tested the autonomous landing algorithm on last year's platform, Athene. After feeling confident enough and with fine-tuning, we performed the full autonomous landing with the Strix system. Autonomous flight and waypoints. To allow good performance when navigating through waypoints, 3 key controllers were tuned to show good plane-specific behavior. Text controller, total energy control system, attitude hold PID controller, and L1 navigation controller. At the beginning of flight tests, manual override was used during takeoff and landing, meaning that out of 25 minutes of flight, 22 were autonomous and 3 manual. After team practice and success of autonomous takeoff and landing, we succeeded to fly for the first time ever a full 25-minute mission without the intervention of the safety pilot. Obstacle avoidance. This year, we developed a new and innovative method for the obstacle avoidance algorithm. This method belongs to the series of the sampling-based motion planning algorithms. The Strix system uses the rapidly exploring random tree, RRT, algorithm as the basis, and its extension, called the RRT star, which aids in finding the most optimal path, a trajectory between the waypoints that minimizes the cost function, subject to given constraints. The process can be performed at any time and takes into consideration the waypoints that the platform is about to move along. Taking the fly zone borders into consideration, we can examine each sequential pair of waypoints for collision detection. The algorithm is then run on those waypoints in which the detection returns a positive result. Image processing. To make sure that our system processes images well, we wrote a code that creates targets so we will have thousands of measurements to test. We trained the system with a simulation that takes photos from the Strix flight tests. To ensure the best resolution for our photos, we tuned their algorithm based on prior Strix training, and when the Strix is about to enter the scan zone, we take pictures to do the fine-tuning. Thanks to our process, we get the average resolution for the photos at 24 megapixels. Detection and classification. We have both manual and autonomous detection. The manual object detection is done using the imaging console, IC. Images are taken automatically and continuously throughout the flight, and thumbnails, reduced images, are sent from the UAV to the IC in order to reduce the bandwidth required per image. The autonomous detection is based on a deep learning algorithm. The system comprises several subsystems. The first one is responsible for suggesting possible targets, and the next one for character classification. In the event of detection, the image location is calculated automatically. Localization. To ensure that we have an accurate location, we take in every flight that the Strix makes an accurate point of the target and compare it to the results given by the algorithm. Then we can tune in and get each time a better result. Our average deviation is 12 meters, 40 feet. Airdrop test. This year's airdrop mission requires us to maintain 80% of the content of the bottle. In order to soften the impact and to avoid bottle eruption, we tested few types of materials and methods. After several dropped attempts, we decided to attach a damping material to the bottom of the bottle, and in addition, we created a small hole in the cap of the bottle in order to release the pressure built in the bottle during an impact. Subsequent to all development experiments of various subsystems and testing performance of each subassembly, we performed several intensive flight sessions in which full system simulation as a whole were conducted according to the competition requirements. During this flight session, the flight line crew practiced teamwork while learning and training according to principles of CRM, Pure Resource Management. This experience greatly improved the team's performance and contributed to operational excellence. These sessions were summarized with a full go-no-go test, testing the crew and system readiness for the competition in front of our faculty advisor who serves as a judge. Performing an overall of 45 flight sessions that sum up to approximately 100 flight hours, these numbers give us confidence in the readiness of the system and the readiness of the flight line crew. See you in Maryland!